youth soccer players that were born early in the year are more likely to be successful elite players. So that means if you're born early in the year, you're more likely to become an elite youth player in Germany. So only January, February, March, whereas in the last 4 or 3 months, you basically you have no chance to become an elite player. So they actually, that was actually real research that was being done, and they came up with all kinds of possible hypotheses where that could be the reason. You can read it up in the book. It's actually kind of interesting, but it's rather, yeah, debatable research. Let's put it that way. So essentially, what you do now is you're creating now the 2 cohorts. Time of the year would be the cohort. So you have early and late. So basically, you have January, February, March, and then you have October, November, December. So you know that, and that comes out of the text, you have 52 elite players in the first 3 months of the year, and you have only 4 in the last 3 months. So that's your observed. So this is information that you would need to be able to derive from the question if if you face such a question. What would be the logically expected count? Because you have a total of 52 and 4, that's 56. So your expected count would essentially be 56 divided by 2. And that's 28. So your expected count is basically 28 in both of these cohorts. And now it's really simple, right? Because we have our formula here. So the only thing we need to calculate is now observed minus expected divided by expected squared. Summing this up will basically get us the chi-squared. So now we know, that was a little earlier, we know from this chi-squared table that our cutoff value for an alpha of 5%, degrees of freedom. How do we calculate degrees of freedom? So we have degrees of freedom rows and columns. So degree of freedom is below. Degree of freedom row is 2 minus 1. It's 2 rows minus 1 gets you the degrees of freedom. Degrees of freedom column is again, is actually 1. Is actually 0. But so the degree of freedom that you would assume for a 2 by 2 table is 1. So your degree of freedom chi-squared is 1. So it's actually, no, it's 2 minus 1 because you count the expected 2. That was the trick. So 2 multiplied by 0 is obvious. 1 multiplied by 0 is obviously 0, but you count the expected as well. So now calculating, so if you just calculate observed minus expected, you basically get observed minus expected, that's 24. You're doing the same here, that gives you 24 minus 24. Squaring this gets it in the positive. O minus E squared. It's not a squared. And now all you need to do is O minus E squared divided by expected. That's now this divided by expected. And so degree of freedom of 1, you have a cutoff value of 3.841. And if we're summing this up and we're deriving our chi-squared, we're basically having a chi-squared of 41, which is substantially larger than our cutoff. So therefore, based on this data we have at our disposition, we are seeing a rejected null hypothesis. So based on this data, we would assume that elite soccer players are more likely to be born in the first 3 months of the year. Do we really believe this data? Probably not. Because what's the problem? We're only seeing elite use players and we're basically going retrospective on when they were born, but we're not taking into account how many elite use players were from the actual period, or whether there were non-elite players that didn't make it to elite and basically also were born in the respective year. So maybe there was just some other factor in the game. But basically this would be the calculation of how you calculate the chi-squared and how you would basically approach this data. Any questions to that? That's the goodness of fit. So that's considerably simple. It's getting a little bit more interesting when we move on to the next example. But let's go along with Noren and Heinzen's slides. So we're seeing here. So here we have our 2x2 tables. That's 2 columns, 2 rows. We have the 52, 28, 4, 28. We're calculating now our observed minus expected square divided by expected gives us the 20.571. And we are by far rejecting the null hypothesis. So the second level of the chi-squared is with more than 2 groups. So this is where we're getting now in the realm of 3x2 tables, 4x8 tables. So it can be quite extensive. So you can expand your tables, your so-called contingency tables. The concept remains the same. You again have 6 steps. You identify your population, your distribution and assumptions. You state the null hypothesis. You determine the characteristics of the comparison distribution. You determine critical values. You calculate and you decide. So the comparison distribution is again the chi-squared distribution. And the hypothesis test is a chi-squared test for independence because we have 2 nominal variables. So now the null hypothesis are here clearly that one group is the same and the distribution of the individuals in your cohort is identical between all groups of the independent variable. What is the dependent? What is the independent variable? This is the example that Noren and Heinzen have put forward, and I like this example. Let's assume the situation that you want to have a corporate intervention. Let's say you spend a lot of money on waste. You're owning a coffee chain, a nationwide coffee chain, and you notice that there's a large volume of waste in your facilities, where customers drink your coffee and they're throwing that cup afterwards in the trash. So now recycling, A, it's more economically, and B, it's also more economic and fiscally and economically, but basically ecologically and economically. So it's greener, and it's cheaper to process. You pay less money for trash and for the trash disposal. So you want to encourage your customers to recycle the cups rather than put them in the trash. How could you hypothetically do that? You could do it with interventions that you basically print their name on the cup. Because if somebody reads his or her name on the cup, it may hypothetically be possible that he or she is more inclined to recycle it rather than trash it. And that's this example, that's 17.2. So that was actually a randomized controlled trial where they basically randomized that cup that went back to the customers, whether it was labeled with the correct name of the customer, whether it was labeled with a misspelled name, or it had no name on it. So they then went on and looked whether the cup was recycled or whether it was put in the trash. So this is a randomized controlled trial. It's in a randomized setting. So you have two independent groups. These were independent observations, independent subjects that were part of this study. And all of these basically had one cup. And this is the example we're going to be working with today. So, and I really like this example. It's a very beautiful example. So we have so 53 were given a cup with a name on it. These are these 53. 53 were given a cup with an incorrectly spelled name, and 53 were given a cup with no name on it. So basically, this was the distribution of the respective groups. So your independent variable is your group allocation. The independent variable is organized as a row, whereas the dependent variable, the outcome variable, is organized in columns. So now we know already that essentially the total for each group is 53. So this is 53 for all three groups. And these calculations out there are called the marginal totals. And that's important to keep in mind. So that's a technical term. So the marginal totals are basically on the outer side, these totals. They basically total up the respective rows and the respective columns. So out of just looking at this, you're seeing a difference already by the naked eye, right? So you see a difference between recycled and trash, and you see that more individuals, almost double as many individuals, have trashed their paper cup. So now we want to know whether there is, and this is where chi-squared becomes a very powerful tool, because you could say, okay, so double as many went in there, but we don't know about the allocations within the respective group. So we need to see whether there's an association between trashing your cup and having a name on it, having your name on it, or having no name on it at all, or a misspelled name. So the marginal totals allow you to actually get there. And yeah, and to get this in shape, you first need to find out, and I'm just putting this here as a reminder. So this calculation is, again, we're calculating chi-squared in the same fashion. We have observed minus expected squared divided by the expected counts. This summed up is your chi-squared. So what do we need first for that? So we need the respective counts. So this is observed, right? So we have the observed counts. We can just arrange this simply. And these were recycling. These were trash. So basically, what we need to determine now is expected. And how do you get expected? So remember the null hypothesis. The null hypothesis says we have observed 52 recycling their cup. We've observed 107 trashing their cup. Now we have three different groups. If there's no association between the observed action of trashing or recycling the cup, the distribution between these three groups in the independent variable would be equal, right? It would be identical for all three groups. So therefore, the calculation of the respective expected count is now the total of what was observed divided by the number of groups. So in the case of recycling, there would be 52 divided by 3 groups. And that would be true for all 3 groups. There would be 17.33 would have been expected to recycle in the respective category. So now the same exercise for trash is now 107 divided by 3. That gives us 35.66. So if there were no association between trashing your cup and the 3 groups, each group would be 35.66. And from that point on, it's easy, right? So we have now observed and expected. And now we just need to calculate O minus E, which is basically observed minus expected. Then it's O minus E squared. Then it's O minus E squared divided by expected. So that's basically this squared. And this would be this divided by expected. Now we just need to pour this all the way down and calculate the sum. And that's our chi-squared. That's how simple that is. Now the only thing we need to determine is not degree of freedom rho. That is 3 minus 1. Degree of freedom column, that's 2 minus 1. And degree of freedom chi-squared, oops, 2 minus 1. And degree of freedom chi-squared is now 2 multiplied by 1. That's 2. So our degree of freedom here is 2. With a degree of freedom of 2, we are essentially looking at a critical value of 5.99. So the critical value is 5.99. So is our chi-squared exceeding the critical value? Yes, it is. So we do have a significant result, and we're rejecting the null hypothesis at a p-value of 5%. That's interesting, right? So basically, again, so we have observed versus expected. We do have 2 groups. So this is now the tricky part, right? You need to extract the information of what was being done. So they have, you need to extract those. So you have all participants, 53 were given a paper cup, 53 were given a cup with the name spelled, 53 were given a cup with no name. So these are the 3 groups. That's the independent variable. Then it was recycled or non-recycled. And this is where you get the data from. So you get 25, 13, and 14. And this is how you have to look at this. So then this question challenges you because you need to calculate then the observed for the trash group. So you need to calculate the difference. So you need to read these questions very, very carefully. So you have a calculation of the marginal totals gives you then the difference between the marginal total and the observed group. Calculating the marginal totals allows you then to calculate percentages. So you can hypothetically, you can also calculate all of this as a percentage. So if you carry this now over here, and you're saying, okay, I have a marginal total, it doesn't always have to be a marginal total. It can also be, okay, now I'm going too fast. But basically, so we're getting also to relative risk, which is a lot of fun and a very useful parameter. Okay, so you calculate based on that, you bring observed into one column. You calculate then expected, and expected is based on the marginal total. So you know what the respective number was for all three groups. You calculate your marginal total. You divide it by the number of groups or levels of the independent variable. Then you know what the number would have been if they were equally distributed amongst these three groups in your respective observed column. And then you just need to calculate the difference between observed minus expected, the squared version of observed minus expected, and then you divide it by your expected count. You get basically, in the greater scheme of things, you're creating a squared deviation, and you're calculating this in reference to your expected count. Summing this up gets you to a chi-squared, which you then compare against the critical value. If the critical value is exceeded, then you have a rejected null hypothesis. So now, okay, let's go with Northern Times. Okay, so this is the degrees of freedom calculation. Degrees of freedom we just talked about. P level of 5%. Yeah, determining the appropriate expected frequency is the most important part of the calculation of the chi-squared test for obvious reasons, right? So you need to know what is my dependent variable, what is my independent variable. And the simple way of looking at this is basically your dependent variable is the one which is basically your outcome. This is the non-modifiable part of it. So if you have observed versus trashed, this always goes as the column. Same with disease versus test. Always in the column, you have the disease as the non-modifiable outcome variable. So you're calculating this as exceeding your critical value, therefore you're rejecting the null hypothesis. This is the calculation we just did. And you are rejecting your null hypothesis. So the difference between the observed frequency and the expected frequency divided by the standard error can also be called the adjusted residual. Why do you need that? Because it gives you an idea of how much this essentially exceeds in the respective cell. We will discuss the adjusted residuals on lab day. There will be no questions if we're asking you to calculate those adjusted residuals, but it basically gives you a proportional, it gives you a way allocated and accounting for the respective cells. It's distributing in, and it gives you kind of a standardized way of looking at your counts and your count differences between observed minus expected. So what is also important to understand is, like, if there are differences, how different are these values observed minus expected? And you're doing this with Kramer's phi or Kramer's phi. So if you're calculating this, this is that large. So you basically, you have here the square root of chi-squared divided by your overall n multiplied by your degrees of freedom of row and column. So your degrees of freedom chi-squared. So your Kramer's phi is essentially here square root of chi-squared divided by your overall n, which is the sum of these two, multiplied by your degrees of freedom, row and column. So this is basically 2. So your Kramer's phi is here 0.15, which essentially is here when degrees of freedom row in column is 2, which we have 2 multiplied by 1, so that's 2. This would be somewhere getting close to medium size, effect size. So there is an effect, a small effect, but it basically doesn't get larger than small. What's also interesting with a contingency table, and this is where this becomes very useful in the world of epidemiology, not only are you looking at counts, so obviously counts are simple, right? But you can also calculate this as a proportion. So you have so-called conditional proportions. And how are conditional proportions being calculated? By basically looking at these counts and calculating based on these counts. So we don't need this. So you're basically calculating with the sum of all of these as a total. Sum these two. With the sum of these as the denominator. So you calculate correctly spelled and recycled divided by your overall sample size. So calculating this through, oops. No, just in the group, sorry about that. It's actually not M8, it's J8. So 47.2. Oh, conditional probability. No, it's calculating this. Sorry for that. It's calculating this as a proportion of the total in the respective group. So there are various ways how you can look at this, obviously. So you could hypothetically, you could calculate it as a fraction of the respective cell in reference to the total sample size. You can calculate it as a fraction or proportion of the actual dependent variable group or the level of the independent variable group. So the conditional probability that proportion that Norneth Heinzen proposes here is basically as a proportion of the marginal total of the respective level of the independent variable. Yes, Freddie.
Fast when you did that formula. How do you pronounce that symbol?
Phi.
Phi.
Phi. Phi. It's the Greek P.
That's the effect size for the chi-square.
That is the effect size for the chi-squared, correct. So now we have our conditional probability. So we have now 25 over 53. We have 28 over 53. We can actually unlock here the row number. And we can just pull it down. And the only thing you need to do, you're basically calculating the proportion in reference to the actual marginal total. So once you have that, why is this important? This is quite important because hypothetically you can then arrange this very nicely in as a bar graph, which essentially allows you to really kind of get a good visual representation of the data. And that should be something we could easily pull off. So we're going to insert bar graph. No, not like this. Like this. I was on the wrong graph. That's fine. Select bar graph. That should give you here the bar. So this is basically the bar graph that Nolan and Heinzen show. So you see here the differences between the respective groups. So that was recycled or spelled. So it automatically recognizes the contingency table format. Okay. So now one way to compare these percentages too is by calculating. Well, let's let me get to that. This is a simpler graph. You can also show only the respective probabilities rather than putting them next to each other. A different way to look at this is so-called relative risk. So in the end of the day, all of this is a probability, right? So you have the probability of a cup ending up in the trash or not, compared with 3 different groups. So what you can do now is you basically calculate the respective risk of a cup ending up in the trash or not. And you do know, and this is now where it's getting a little different to look at this, because essentially what you have here is a probability. So when you consider probability as a percentage ranging from 0 to 1, the percentage that you have observed in your group is consistent with a probability of something going in the trash or not in the respective group. So if you sample 53 individuals and 28 of them throw their cup in the trash out of 53, the probability is 28 over 53, as we have calculated here with the conditional probability. If you do this with 1,000 people, you have 520 cups that go in the trash, or 528 cups that go in the trash, as compared to 472. So you're basically following the law of large numbers. Every probability, if you do it in a larger sample size, will translate into an actual count of cups that go in the trash. And these differences, so now let's go and take a step back. We are looking at an intervention that is being rolled out in our nationwide coffee chain. And if you sell per day, let's say 20,000 cups, and there's a difference of 5% or 2%, that's a lot of cups. If you pay now a difference of 10 cents per cup that either goes into waste or goes into recycling, and you save 10 cents if it goes into recycling, you make a tremendous difference, right? So it does make a difference, let alone what you essentially do good for the environment by having more recycling. It's kind of it's a fun exercise, right? But this is statistics and research at work by basically testing hypotheses like that. And this is where research becomes an interesting use case, right? And you can use various use cases for that scenario. It's like you have randomized controlled trials for 1 million different things, and a randomized setting allows you to minimize confounding, right? So you have an equal, and this is where randomization is so important, because if you have here, for example, in one of the groups, you have like 20 people in there that are by default already more environmentally friendly and will take the paper cup and never throw it in the trash in 1 million years, but rather put it in recycling by default, you have confounding in one direction. So you couldn't interpret this result anymore. So randomization allows you to have an equal distribution of environmentally friendly people versus those that don't care. So now thinking about probabilities. So we have 53 individuals. Out of those 53 individuals, 28 threw their cup in the trash. So you have a probability of 53% of that cup going into the trash when the name is correctly spelled on the cup, compared to 74% if there's no name on it at all. So there's a huge difference in the probability. So if you want to utilize an alternate way of looking at this is to basically determine an outcome that you do not desire. And that outcome is that the cup goes in the trash. And you can then relabel probability for risk. So let's assume this to be a risk. So the risk of a cup going in the trash for the group where the name was spelled correctly is 53%. That's the risk, 0.53. The risk of that cup going not or going in the trash for those where the name was misspelled or there was no name on it is now, it gets a little trickier here. So let's do the sum of incorrectly spelled and no name as our reference category divided by the sum of all these individuals that have gotten a cup. So this gives us a 74% risk. So in those individuals where the name was not correctly spelled, the probability or risk is 74%. What does this tell us? That the risk is higher in those where the name was not correctly spelled. If you want to calculate out of that now something different, you can do two different things. You can calculate a risk difference or a risk ratio or relative risk. And this is one of the most commonly used ways of depicting the differences between the risk in respective groups. Particularly the relative risk is a very important marker of determining the risk of a population as compared to a reference group. So if you want to quantify now the risk difference, it's basically, it's the risk of incorrectly or no name minus your group with the correctly spelled name. So the risk difference is 21% or 22%. So there's an increase in risk by 22% if the name is not correctly spelled or there's no name on it at all. If you want to look at it as a risk ratio or a relative risk, you're taking the risk from your non-favorable group with the higher risk, and you're dividing it by your reference risk. That's 53. So what you have here is 1.41. What does that mean? That means that the risk of the cup ending up in the trash is with no correct name or no name on it, is 1.4 times the risk of going into the trash if the name is spelled correctly. So basically you can multiply the base risk with that relative risk, and you get to that risk of the group with no name or incorrect name. So these two are extremely important to keep in mind. And Noren and Heinzen also indicate that. So we can quantify the size of an effect with chi-square through relative risk, also called relative likelihood. So risk and likelihood is used synonymously here. By making a ratio of two conditional proportion, we can see, for example, that one group is 3 times as likely to show some outcome, or conversely, that the other groups is 1/3 as likely to show that outcome. So I used here an extreme case, so we have here 1.41. And the beauty is that if you want to compare these risks, I compared the risk of incorrectly spelled name and no name. You can also do this simpler. You can just compare group 1 versus group 2. So you can say, okay, any name, or you can also compare the relative risk. Okay, so risk Comparison 1, 2. So we're comparing now correctly spelled name versus no name. It's this. So now the risk ratio is basically this divided by this. So this is 1.39. So there's a 1.39 times higher risk to find the cup in the trash if there's no name on it compared to a correctly spelled name. So it really depends on which reference group you're using. So you have a numerator and a denominator. The numerator basically is that drives the ratio. The denominator is your quote unquote reference group. So you're putting the numerator in reference to the denominator group. An alternative interpretation is here 1.39 would also indicate there's a 39% risk increase compared to the reference group. So that's relative risk. So keep in mind, so we have now, so first exercise was an example like this is to extract the information that you actually want to have. And that's essentially is how many people in each group. So we know that's a randomized setting, so it's equal size in each group. So we have 53 individuals in each group. That adds up to 159 in total. We know now the number, we have 13, 25, 13, and 14. That gives us 52. The resulting difference is 107. And they are to be determined based on the marginal totals. Know the marginal totals. I recommend to always calculate marginal totals in examples like that because it makes things a little simpler and it kind of makes it a little bit easier to grasp. Then we're basically bringing our data in shape. We have observed, which comes from our contingency table. We have our expected, which are basically calculated from the marginal totals of the respective column. That's important to keep in mind. So this is here the angle you're looking at this. So you have 52 individuals. You have 3 different groups. Gives it 17.33. We have 107 here in the trash category. Divided by 3 gives us 35.66. Then we calculate observed minus expected. That gives us basically this deviation. We're squaring the deviations. We're taking the squared deviations and dividing it by the expected count. We're summing it up and we're coming to the chi-squared. In the knowledge of our degrees of freedom, we can now quite simply determine the degree of freedom chi-squared by calculating the degrees of freedom row with degrees of freedom column. The critical value allows us then to drive our decision to reject the null hypothesis. In our case, rejecting it. If it were below, we would not reject it. You calculate then, in the next step, you're calculating your conditional probabilities. So the conditional probabilities are here, as per Noren and Heinzen, put in condition to the marginal totals of the respective levels of the independent variable. We're calculating these probabilities for each of our groups. Logically, the sum of these probabilities needs to be 1. I think that's quite logical. So this needs to add up to 1. And we can then utilize these conditional probabilities to create a bar graph. I'm sure I've lost one. Oh no, here it is. We can simply create a bar graph by just selecting our table, going on insert, and no, bless you. Find the respective bar and map this out. And then essentially we can quite swiftly create such a bar graph. We can calculate Cramer's phi to see what the effect size is. The actual conventions are stated here. Where is it? Yep. Here is the effect size convention. So 0.1 to 0.3 is small, 0.3 to 0.5 is large, 0.5 and greater is large if we only have one degree of freedom row and column. It's here stated for 2 and 3. And we can now also use these conditional probabilities that we have calculated to essentially also calculate the risk in the respective group as a reference as we choose it. We can either do it in reference to only one group or to an entire group, like I did, by summing up all that was trashed in incorrectly spelled and no name, divided by the marginal totals of these two groups. Gets us basically, gets us either a risk difference from one group to another, or gets us a risk ratio. Again, these are two inherently different markers of comparing risks. Risk difference is less often used. Risk ratio is really the most common one. And the interpretation is the number of times the risk of one group is greater than the other group. Or alternatively, you can calculate this risk ratio -1 and you calculate a certain XYZ% increase. In that case, it's a 41% increase in the risk. Okay, any questions? Well, make sure to review the lecture. I will post this tonight and make sure that you have access to it because it will be part of the quiz on Wednesday. So please review chi-squared. It's a very simple test. That's why I have no bad conscience about giving it on Wednesday. It's a simple test. It's a simple arithmetics. It won't be as complicated what you need to calculate, but you know how to operate it and how to look at it. All right. Thank you very much. Have a nice evening.
Thank you.